Oye, Añuloda. I've been meaning to make a video like this for a little while. Technically, I want my next QR2 series to be based around power systems and recharging, but right now, life is just too busy for me to try and build some scenarios and the lessons that go along with that. So, with semifinals, as of the filming of this video, semifinals right around the corner, I know many of my teams were still having issues with doing the calculations to properly recharge a battery or manage the power systems in general on a satellite. So, I wanted to have a lesson of some kind that kind of gave a rundown of what these numbers represent and how to work with them. So that's what this video is, and it will stick around at least for a while until I get a replacement one tied to specific scenarios. That being said, in this video we're going to take a look at power and recharging for your systems for a satellite. Now this includes a little bit of talking about batteries, but the main thing about it is we'll see how you can determine the capacity needed for a battery, and most importantly, how to get solar panels big enough to supply enough power for your satellite, and also to recharge the battery, which I believe a lot of teams were having trouble with. Okay. So the first thing that we want to understand is this. The technical term for it is called flux density, and when we're near the surface of, or not near the surface of the Earth, but near the Earth, we more broadly have a technical term titled solar constant. Now, I'd forgotten, I've always used solar constant just as what the local flux density would be, and I call that the local solar constant. So if I've made reference to that in previous videos or in other videos or lessons, technically I'm a little bit off on that, because the solar constant is defined to be the flux density for a star at 1 AU from that star. Now that's a bunch of astronomy stuff, but basically the solar constant really only is technically correct if it's around Earth's orbit, talking about the sun, or the equivalent location in another star system. So the technical term is going to be flux density, but I'm also probably going to forget that and go back to solar constant, which is what I remembered anyway, so I'm probably going to use those two terms kind of interchangeably. Flux density is the more correct. Okay. But what does all that mean? Fancy terms aside, let's talk about what it actually represents. In short, the sun's super bright and it gives off a lot of energy in the form of light. And so if you've got something super close to the sun, it's going to be hit with a lot more light. So in my diagram here, I actually made basically a representation. Here's our sun, and we've got light rays coming off of the sun. Now, the more light rays that hit an object, the more light would be hitting it, is kind of the visual representation I'm going for. So close in, we have all of these squares are the same size. So for an object of a specific size, if it's close to the sun, it's going to be hit by a lot of light and therefore be receiving a lot of energy. If you've got something a moderate ways out, this one only has 2 light rays that are hitting it. The way that I'm representing it, it'd honestly be a lot more light comparatively. Pardon me. But this kind of gives you a visual that as you get farther out, the way light works, it's going to spread out and you end up with less intense light. Same thing happens if you're looking at like a lamp, for instance. If you put your eyeball right next to the lamp, don't do that, because that's so much energy and you're so close in that it can actually damage your eye. You might also be able to feel warmer by being that close. Maybe put your hand close to it, but I wouldn't necessarily touch it. You'll actually feel a little bit warmer from the light actually having energy and your hand absorbing that. As you get farther away, the light gets less intense. You won't feel the warmth, and while it might still be unpleasant to look at, it's less likely to damage your eye. And if you look at a lamp from down the street, you could probably look directly at it and it won't hurt your eyes because you're so far away that you're only getting effectively 1 light ray, whereas when you're super close, you might be getting, well, my representation here is 3 light rays, but in reality, with the actual distances involved, you might be getting 1,000,000 light rays. So there's a big difference there. Depends on how far out you go. Okay, so that's kind of the idea of the energy that is being put out by the sun, and all of that is in radiant energy, in other words, light. Next up, if we want to replace that instead, and, well, not replace the idea, but take these squares and replace them with a satellite. So I've drawn a diagram of maybe a satellite here, where you've got the satellite here and its solar panels here, and we want the solar panels to collect some of that light. when it collects that light, solar panels, the way that they're designed, can turn that light energy into electrical energy to help our satellites actually do the things we want them to. Now, the sun's light provides about 1,360 watts per square meter. That's not an energy, that's actually a power per area. And it does that across what's called the entire electromagnetic spectrum. And that value corresponds to being as far out from the sun as Earth's orbit. So if you were closer than Earth's orbit, that number would be something different, probably bigger. And so if we were around Venus, then the flux density would be significantly higher, maybe like 1,800 watts per square meter. I'd need to look it up. But if we were farther away, say at Mars, it would be lower. So we might end up with maybe 1,000 watts per square meter. And if we went way out to, say, Neptune or something, really far out there, we might be down to only like 100 watts per square meter, or even smaller than that. We could do some calculations on it. I think it follows the inverse square law, but that's not what this video is about. So basically, what that number means is if you have something as far out as the planet Earth, or in other words, in Earth orbit, if you have something that is 1 meter by 1 meter, it could collect upwards of 1,360 watts of power if it were 100% efficient. That basically means if it were possible for it to absorb all of the light and turn it into useful energy, that's the most energy, well, power that it could get. We're going to talk about the difference between power and energy in our next slide. But due to a variety of factors, no solar panels that we have are 100% efficient, and probably never will be. As much as it seems like, hey, we should be able to get really high efficiency, first off, the electromagnetic spectrum is really big, and it's hard to get materials that can absorb both far IR, heat vision stuff, and all the way up into X-rays, which maybe, I think the sun does give off a moderate number of X-rays, though UV is usually where more energy is going to be. Based on our star, it peaks in the green portion of the visible spectrum, so most of the energy is going to be around the visible spectrum. If we have a good semiconductor that has good band gaps related to that energy level, I'm throwing a bunch of words at you, but basically, fancy solar panels that are really good at collecting energy, they'll still only probably range from the near infrared, maybe bordering into the far infrared, and into the nearby UV. I forget all the UVA, UVB, and so forth, at least into the UVA. But in short, it's very unlikely with material sciences, unless we find something in the future that's super awesome, to find something that can absorb all the different types of light, and therefore we wouldn't get 100% efficiency just based off of that. There are other factors in nothing is going to be perfectly efficient in turning light energy into electrical energy. We have things like the laws of thermodynamics that, so far as we know, limit exactly how, or limit the top efficiencies that you could get. And so, in short, I don't want you to think that we're just quitters at this and we just haven't come up with great ideas. We've got plenty of great ideas, but we're still limited to pretty low values on the efficiency. Real values, I think the highest that I recall seeing are somewhere in the 40% range, and those could be super expensive. You'll also find that the higher efficiency solar panels have to be made with more specialized material, and they may cost a lot more compared to the ones with low efficiency, which brings in some of the design that you all would do. Okay, now that we've got an idea about the solar panel efficiency, it describes how much of the incoming radiant light can be turned into useful electrical energy. Now let's talk about the units that are probably going to show up in your analysis. The watt hour. Capital W, lowercase h is usually how this is abbreviated. Now, a watt measures power, which is energy divided by time. Pardon me. In fact, a number of my students, possibly watching this video, will be tested over that next week in our AP Physics class. But in this case, I want to get that across because power and energy are not the same thing. Watts is not the energy that's actually going into your battery. It describes how quickly you're getting energy. Energy divided by time. So in order to get the energy collected or stored, we need to take a power and multiply it by a time. This is where we get watts times some time unit. Usually hours, but sometimes minutes. You might want to use watt minutes instead. That's another way of working with it. If you multiply a watt times a second, you would end up with the SI unit called a joule. And that's the thing that we usually study in our introductory physics classes. But a joule is super duper tiny. And so for a lot of the energy that we want to talk about, we're talking about larger values of energy. So the watt hour is probably going to be the most useful unit for you all to do analysis in Stellar Explorers. When it comes to a city power grid, they actually commonly use thousands of those, which would be a kilowatt hour. Your electric bill that is sent out for power that you consume is actually based off of kilowatt hours. Okay, a watt hour is literally just a watt times hour. So if you had a 100% efficient solar panel and it was 1 meter by 1 meter, it would collect 1,360 watts of power. If the panel is in sunlight for an hour, it would collect, well, the power that it receives, 1,360 watts, times the time, 1 hour, which is 1,360 watt hours of energy. Energy is the actual content that goes onto your battery. Power is how quickly you use that energy. We could also write that as 1.36 kilowatt hours. I'm bringing that up here, but we won't talk about it again in this, but it does connect to real-life applications. I recommend working with watt hours, or maybe watt minutes, whatever is most comfortable for you, though most of the analysis in this video lesson will be based around the watt hour for simplicity. Also, from what I've seen, I think most of the times that we're given battery capacities in the scenarios from Stellar Explorers, they usually rate the battery capacity in watt hours, and rightly so, because it's honestly a really convenient unit for it. If that panel did not have 100% efficiency and only had 50% efficiency, that means instead of getting 1,360 watts of power, it would only get half of that. 50% is half, and so we would end up with 680 watts. In 1 hour, that would equate to 680 watt hours. And then if it only collected 25% efficiency, then that would knock it down to 340 watt hours. Again, take your watts that you're getting and multiply it by the hours, and you end up with watt hours. So our general equation would look like this. ECOL equals GSC times eta times A times T. Well, that's a lot of variables to throw at you, so why don't we explain what those are? Here's our general equation, and the one that I will use a lot during this lesson, so hopefully it's one that's useful for you. But E sub col is the energy collected in the appropriate units. Now I say the appropriate units, the units you get are going to be based on the units you use. If you put in watts and hours and meters, you're going to end up with watt hours. Or if you use watts and minutes, you'll end up with watt minutes. So just track your units in there and make certain that you're consistent. In this case, E col is the energy that we collect, or possibly use, although for this equation, this is the energy that is collected by the solar panels. G sub CS, I'm using the notation that it corresponds to the solar constant, but it's going to represent the local flux density, or the solar constant describing how intense the light is. I'll give you a hint, that value will be measured in watts per square meter. So if nothing else, if you see a value that is in watts per square meter, there is a very good bet that it is your local flux density, and you would put that number in for G sub CS. We're going to multiply that by eta. Eta is that little letter here, Greek letter, looks like a stylized lowercase n. But that's the common variable that is used for the efficiency of a system, in this case, the solar panel. It's usually given in percentages, but divide that number by 100 to convert it to a decimal for your calculations. We'll see some examples of that here in just a minute. Capital A is the area of the solar panel, usually in square meters. All of this is going to be based on the units that you put in, but I think all of the ones that we've been working with have been in square meters, and that matches kind of the standard when designing these things. And you all have control over that area. So sometimes you'll be asked to just say what is the area of solar panels you want, or sometimes you might be asked what is the height and width of your solar panels, and you might have to do a little bit more math on it. In this case, I'm just going to work around the idea of the area, how many square meters you would need. And finally, T is the time that your solar panel is in the sunlight. Now that's usually in hours, but depending on what units you're pulling, it might come up as minutes. So this is our equation, these are the parts that go into it, and a rough idea on how to use them. Okay, so your power needs. When you're designing your satellite, go through and find all the things that require power. And since it's power, they should all be listed in watts. You want to add all of those up. Now, if you, whatever number you end up with, I'm giving you an example in just a moment of, let's say you add all those up and you find that you need 1,572 watts for your satellite to power everything. That's how much you need the solar panels to supply when the solar panels are in sunlight, just to keep the satellite running. If you have less than that, then you're not supplying enough power and some components will have to shut down, which could be dangerous for the satellite. Let's say that you are consuming 1,572 watts for your satellite and it's doing that the entire time that it's on, which is basically forever, at least for our scenarios. We're planning for the long term on this. Let's say the local flux density is 1,360 watts per square meter. That's supposed to say watts per square meter, so I made a mistake on that, sorry. But basically, we're going to say that it's in orbit of Earth. And your solar panels have an efficiency of 15%. In other words, 0.15 will be the number for eta. In 1 hour, you will need an energy of 1,572 watt-hours, your power times time. We can fill in our equation. Our energy collected equals our flux density times our efficiency times our area times our time. Now, I will say this real quick before we start filling in some of the numbers on that. This is one way to approach your power needs. This isn't the only way. You could set up a different equation. I've solved it different ways as well. But I think keeping track of the energy could actually be very useful for a couple of reasons, and that's why I've decided to show you that approach in this video. Okay. The energy collected, the energy we need, is 1,572 watt-hours. Remember, energy is power times time. So that's watt-hours. Well, that will be equal to our flux density, which is 1,660 watts per square meter, times our efficiency, which is 15%, 0.15, times the area of the solar panels. Well, we don't know how much we need. That's what we're after, so I'm going to leave that as A. And then I'm going to say, okay, well, this is running for 1 hour in our scenario, or in our example, so I would multiply by 1 hour. I can then do a little bit of algebra that I'm going to leave to you, and I find that the area that I need for my solar panels to achieve 1,572 watt-hours in 1 hour at 15% efficiency, and the local flux density, is 7.7 square meters. All right. So that tells us the bare minimum to keep the satellite operating, but that's only when the satellite is in the sunlight. When the satellite moves out of sunlight for one reason or another, we'll take a look at that in just a moment, usually because it's going behind a planet or a similar object, then when it's not in sunlight, the solar panels can't actually generate any power or any energy. And therefore, you've got to have something else that keeps your satellite on, or else it'll immediately shut down. In this case, let's talk about a little bit of the definitions. I'm going to take us over to a dummy thing that I set up in STK. This one's just a random scenario that I made and then threw in a satellite for us to have numbers to play with. So I've got a satellite here in an elliptical orbit. I think I've got it set as an equatorial orbit and just played around with it. The settings don't necessarily matter. But right now the satellite is in sunlight. We can see it's above the bright side of the planet, and it's looking back over with the sun back over there. So our satellite is in sunlight. I'm going to press play. It's going to drift around. And one thing that I want to point out is this. Okay, from my view, the satellite is now over the dark side of the planet. So if you're not careful, you might say, oh, well, I must be in darkness now. But that's on the planet. When I actually go over to the satellite and I look at it from its view, which I could zoom in on, but I'm not going to, we can see that it has not gone behind the planet yet. So that's one thing to keep in mind. You can't just look at this by eye, at least not easily. The other thing that I'm going to bring up is this. So right now we are in sunlight, and I'm going to set it up where half of the sun, because the sun is not just a dot here, it has an actual size that we can see, an apparent size. I'm going to press play, and let the satellite drift over here. So if I were to zoom in on it, I don't want to spend a whole lot of time on that, but let's say that the satellite had my view. Right now it can see part of the sun, but not all of the sun. This is the same thing that happens at sunset or sunrise, and we call this penumbra. Since the Earth is blocking part of the sun, we're not getting all the light that we normally would if we're in sunlight. So this is kind of like sunrise and sunset. You're only getting a fraction of the light. And honestly, that light is the amount is going to change. Right when you go into penumbra, you're actually going to have very close to full lighting, but not quite full. And as you're getting to the end of penumbra, you're going to have almost no light as effectively the sun sets from your viewpoint. Now, one of the other things to note is penumbra is usually a very small amount of time. So we're going to come over to our lighting times in just a moment. But if I keep playing, now the satellite has gone very much around the side of the planet, and now it should be in shadow. And then we can end up watching it. Eventually it will come back into sunlight by going through penumbra on the other side of the planet. And this happens again and again and again. So I'm going to speed this up. We've got it zip around. Darkness, light, darkness, light, darkness, light. Okay, so hopefully you get the idea. And I want to emphasize you have penumbra on one side as it's sunset, and penumbra on the other side as it's sunrise. So every cycle, you have sunlight, then penumbra, then darkness, then penumbra, then back to sunlight. So something to keep in mind when we look at trying to solve this scenario. Now, on the upside, penumbra is actually kind of small compared to the other values, as we will see, and therefore you can probably ignore it, but I wouldn't. They don't always tell us whether or not you should consider penumbra darkness or not. I always put it in and assume that it is, because it's such a small amount to include in there. Okay, so how did I bring up this lighting report? I'm going to go ahead and close it real quick. I'm going to right-click on the satellite. I'm going to go over to the Reports and Graph Manager and click on that. And then what I want to go down to lighting times, which is right here, our lighting times report. You can also go with the lighting times graph, but I'm going to go with the report because that has the actual numbers. The graph can be useful to look at periodicity and get an idea, but it helps if you've actually got the report. Now, one thing that I'm going to bring up on this is I recommend that you disregard the first and last number in your list, because you'll notice basically we've got a pattern here. All of the numbers ignoring the first and last is 1.685, 1.685. It starts getting a little bit less with 1.684. These numbers are going to shift a little bit throughout your scenario, but they're not something that usually shifts by a whole lot. We end up with 1.665 by the end of this, and so our largest number that we can see on here is 1.685. Now, our smallest time that we've got is 1.665, ignoring the ones on the edges. So if you go down to the summary, it will give you the whatever number is smallest, but those are the ones on the end. You don't want to include those because the reason that it's so small is that's when the scenario actually ends. What this time period would actually say, if we let it finish, would be 1.665 or maybe 1.664, not 0.428. It just says 0.428 because our timer ends and the scenario stops at this time, so that number is not representative of what's happening to the satellite. Same thing with the beginning one. It's such a small number because the satellite started off in sunlight and therefore we're not seeing the full time there. Regardless, what you want is, I recommend designing your charging systems around the worst number. You can also go in and try and do a complete budget, a power budget, where you, just like with the data we saw in some of our other lessons, you see how much energy is coming in, you put that in the battery, and then you keep track of how much goes out for each individual timestamp. That being said, for power, the big thing that you want is to make certain that you can make it through your worst condition. So look for your shortest sunlight time and your longest. Hey, look at this. We've got penumbra is next up down. And you can see that those are actually really small. Those are going to be 0.005 hours because that's the units that I have my report in. Let's go to our umbra times. What we want is the maximum value, which a lot of times you can take directly from this report. It's got, my maximum value is 0.696. Now, One thing that I like to do is I like to make certain that I plan for a worst case scenario, and I'm going to add on my worst penumbra onto both sides of the umbra. Remember, you have sunrise, sunset, then darkness, then sunrise. So I'm going to take the 696, and I'm going to add on 2 of 0.006. Though I could probably get away with just 0.005 plus 0.006, but I'm going to, again, plan around the worst case scenario so that I've got enough and I don't end up running dry. Okay, so that's how we actually pull these. You can also do an export as a CSV so that you could bring this in and do in-depth analysis on it. But usually with the power systems, a lot of times you can get by just by being able to look at the worst case scenario. So in this case, going back to our presentation, now that we've introduced that, the satellite will, let's see, we talked about umbra, penumbra, and sunlight. In this case, I go through and talk a little bit more about the planning needs for this, but now that we've brought up an actual lighting time, let's jump... sorry. I got ahead of myself talking about the lighting times on that. We'll come back to that. As a reminder, whenever the satellite is on, it's going to need that 1,572 watt hours for, well, watts, and therefore for 1 hour, we would need that much energy. We can find what I'm marking not sunlight time, penumbra and umbra, and add those together to get our worst numbers. So in this case, finishing up with the example that I introduced before we go to the more complex one. If you have only 7.7 meters squared, then you don't generate any extra power in order to recharge the battery when it hits sunlight. So the idea is you have to generate enough power to keep the satellite on, and if you've got a battery to get it through the darkness, you need extra power when you're in sunlight to recharge your battery. If you do not successfully recharge your battery, it's going to slowly drain, and then eventually it'll be empty, and when your satellite goes into the darkness, your satellite will shut down. So to do this, we need to know how long we're going to be in the sunlight, gaining energy, and once again, it might be best to find the worst number. In this case, like I said, the shortest sunlight time, and design around this. So for example, if I'm in sunlight for 1 hour and out of sunlight, in not sunlight, or umbra and penumbra, for a combined value of 1 hour, I would drain 1,572 watt hours from the battery while in darkness. So I need, not Ned, to restore that in sunlight on top of supplying the regular power to the satellite. That means when I'm in sunlight, I'm going to need 1,572 just for the satellite to keep running. And I also need to replace the 1,572 watt hours into the battery that I already pulled. So I can add those two together and say, okay, when I'm in sunlight, I need 3,144 watt hours from the solar panels in that 1 hour of sunlight. Okay, we run through, we do those calculations, and surprise, surprise, we end up with, well, if I need twice the power so that I could then recharge my battery, I would need 15.4 meters squared. In other words, twice the area. Okay, now that we've got that lighting times report, I grabbed a screen grab of it and brought it in here, but you don't have to look over it. We've already talked about those numbers. So let's go to a more applicable example for you all, because you're probably not going to have an orbit that magically has 1 hour in sunlight and 1 hour in darkness. So let's use ones that are possibly more realistic. Let's say that we have a satellite that needs 652 watts in order to operate. We have the flux density of 1,360 watts per square meter, and it has a solar panel efficiency of 22%. And the lighting times are from the report that we talked about. In this case, from that report, the shortest sunlight time, ignoring the ones affected by the beginning and ending of the scenario, is 1.665 hours. The longest darkness, umbra and penumbra, is 0.707. I told you that's where I'm combining the penumbra and the umbra to get those values. So we need at least 1,086 watt hours in energy while we are in sunlight to keep the satellite operating. But remember, that number is just when we're in sunlight to keep the satellite working. In darkness, we're going to then also drain 461 watt-hours from the battery. And I've got the examples on how I'm running through that. So the 1086 is from 652 watts, that's how much power I need to keep the satellite on, times 1.665 hours in sunlight. Well, that comes up to 1086 watt-hours. In darkness, I'm going to drain 461 watt-hours. That's 652 watts that I need to keep the satellite running, times the time, 0.707 hours. So I need to generate a total of, I add those together, 1,547 watt-hours when we're in the sunlight. Okay, so when I'm in the sunlight, now we can go back to our equation. I know that I need 1,547 watt-hours of energy when I'm in the sunlight. Well, here's my solar constant, or flux density. Here's my efficiency. The area is what I want to find. And remember, I will be in sunlight for 1.665 hours. So I plug all of those in, and I solve for it, and I find that the area needed for this satellite under these conditions is 3.10538, and I'm going to stop, or 378. I'm going to stop there. By the time you're going to that many significant figures, round up at least a little bit. I would only go to 3 or maybe 4. I would only go to 3 significant figures and base your design off of that. So that's what we would need on the satellite. Okay. This video is starting to run a little bit long, but hopefully this has been useful for you and gives you an idea on what these numbers actually represent and how to work with them. Once again, this equation, I think, is a very good way to approach it and allows you all to think in terms of energy content. The other nice thing about that is, in this case, if we know that we're going to need energy of, in darkness, say 461 watt-hours under our worst-case scenario, then when I look at the capacity of a battery, I know that as long as it holds at least 461 watt-hours, then we should be good with that battery. I don't necessarily need one that can hold 800 watt-hours. So that's one way that doing it this way will also get you additional information in your design. Okay, I think that's everything that I wanted to go through on this, and hopefully you find that useful in how you can go about not only getting enough power to keep your satellite running, but also predict how much solar panels you would need in order to get a recharged battery. Until next time.